Have you ever really thought about what happens when you flip a light switch? I mean, what's going on inside the walls that makes the room just light up? Well, it's not magic, it's physics. And the principle behind almost every bit of electricity we use is something called electromagnetic induction. It's a fantastic story about a hidden connection between two forces, a couple of brilliant experiments, and a discovery that literally powers our entire world. So let's dive in and see how it all works.
You know, for the longest time, science saw electricity and magnetism as two totally separate things. They were just not related. You had electricity, this strange force that could flow through a wire, and then you had magnetism, this invisible force that made compasses point north and pulled on certain metals. They were just in two completely different worlds.
And then, in the early 1800s, everything changed. Researchers like Hans Christian Ørsted discovered something absolutely mind-blowing. They found that an electric current, just electricity moving through a wire, could actually create its own magnetic field. A live wire could make a compass needle swing around. Suddenly, those two separate worlds crashed right into each other.
Well, this discovery immediately sparked the next huge question. I mean, it's the obvious one, right? If electricity can create magnetism, can it work the other way around? Could a simple magnet just sitting there somehow create an electric current in a wire? That was the mystery that the greatest scientific minds of the day were desperate to solve.
So this hunt for an answer takes us right into the laboratory, where a series of truly groundbreaking experiments would lay the foundation for, well, pretty much our entire modern age.
And the two main scientists who finally cracked the code were these guys, working completely independently right around 1830. On opposite sides of the Atlantic, you had Michael Faraday in England and Joseph Henry over in the United States. They were both about to stumble upon the exact same monumental discovery.
And you know what's amazing is how simple their setup was. All they really needed was a coil of wire and this thing called a galvanometer, which is basically just a super sensitive meter that can detect even the tiniest little spark of electric current. The whole goal was to make the needle on that galvanometer move, using nothing but a magnet.
And what they found was fascinating. When Faraday pushed a magnet towards the coil, the needle jumped. A current was created. But then, when he held the magnet perfectly still, even if it was right inside the coil, nothing. The needle went straight back to zero. And then, when he pulled the magnet away from the coil, the needle jumped again, but this time in the opposite direction. The key takeaway was crystal clear. It wasn't the magnet itself that mattered. It was its motion.
So, the next logical question to ask was, does it have to be one of these permanent bar magnets? We already knew that an electric current creates its own magnetic field. So, what if we swapped out the magnet for another coil of wire that had a steady current flowing through it?
And yep, the experiment worked exactly as you'd expect. Moving the current-carrying coil towards the first coil made the needle jump. Holding it still did nothing, and moving it away made the needle jump the other way. The results were identical. It's all about the relative motion between a magnetic field and a wire.
Now this next part, this is where Faraday's true genius just shines. He started to wonder if motion was really the essential ingredient. Could he somehow induce a current without moving a single thing? For his final trick, he set up two coils, side by side, perfectly stationary. He pressed a key to send a current into the second coil, and for just a split second, the galvanometer on the first coil gave a kick, and then back to zero. While the current was flowing steadily, nothing happened. But then when he released the key, cutting the current off, he got another momentary kick, this time in the opposite direction.
And that was it. That was the ultimate insight. It was never really about motion at all. It was about change. Whether you're moving a magnet or moving a coil or just switching a current on and off, what you're actually doing is causing the magnetic field that passes through that detector coil to change. That change is the real secret sauce.
Okay, so this discovery was incredible. But to turn it into a real, usable law of physics, Faraday needed a way to measure this amount of magnetic field passing through the coil. And that leads us to a really important idea called magnetic flux. Magnetic flux sounds complicated, but it's really not. It's just a way of counting how many magnetic field lines are passing through a specific area, like the loop of our wire coil. So if the magnet is far away, the flux is low. If you bring it up close, the flux is high. It's the key variable that ties everything together. And by thinking about everything in terms of this flux, Faraday could finally take all of his experimental results and boil them down into one single, powerful, and honestly, beautiful mathematical statement. We now call it Faraday's law of induction.
And there it is. The law basically says that the induced electromotive force, or EMF, which you can just think of as the voltage or the electrical push, is equal to how fast the magnetic flux is changing. And that phrase, rate of change, is everything. The faster you change the flux, by moving the magnet faster or flipping the switch quicker, the bigger the voltage you're going to get.
So, we know that a changing flux creates a current. Awesome. But which way does that current flow? Does it go clockwise or counterclockwise? This is the last piece of the puzzle, and the answer comes from another really important principle, Lenz's law.
Lenz's law tells us something really deep about how nature works. It basically says that the new current you create will always generate its own magnetic field that fights back against the change that created it in the first place. So if you try to increase the flux, the induced current creates a field that pushes against you. If you try to decrease it, the induced current creates a field that tries to hold it in place. It's like nature putting on the brakes. And this isn't just some random quirk of physics. It's a direct result of the conservation of energy. Think about it. If the induced current actually helped the change, you could give a magnet a tiny nudge and it would just accelerate off into the sunset, creating free energy out of nothing. Lenz's law makes sure there's no free lunch. You have to physically work to push that magnet against the opposition, and it's that work you do that gets converted into electrical energy.
All right, so we have Faraday's law telling us how much voltage we can get, and Lenz's law telling us which direction the current will flow. When you put those two ideas together, you go from a cool little experiment in a lab to the technology that powers our entire civilization.
Seriously, all of this knowledge, these simple principles, are the direct foundation for one of the most critical inventions ever conceived by humankind.
The AC, or alternating current, generator. This one machine is the direct technological child of those simple little coil and magnet experiments.
And here's the whole idea in action. Instead of pushing a magnet back and forth, a generator just uses some mechanical force to spin a coil of wire inside a magnetic field. As it spins, the magnetic flux going through it is constantly changing, from max to zero to max the other way. And according to Faraday's law, this constant, rapid change in flux induces a continuous flowing electric current. That is how we turn the energy of falling water, or steam, or wind into the electricity that runs our lives.
You know, the story goes that when Faraday first demonstrated his discovery, some politician asked him, "Well, that's all very clever, but what is the use of it?" And Faraday's legendary reply was, "Sir, what is the use of a newborn baby?" He knew he had found something fundamental about the universe, and while he could never have pictured our modern electrified world, he knew that the potential was absolutely limitless. A simple shifting magnet, once just a scientific curiosity, is now the spark of genius that powers our entire planet.